This will introduce our next speaker, Tom Pike. So let's watch the animation. Here we are from our launch pad, looking up at the brightest object in the sky, which, as we zoom in a little bit, turns out to be Mars. And we're going at an incredible rate of speed towards Mars in this animation, a little faster than the spacecraft, which took 10 months. And we didn't slow down quite as rapidly, but in any case, we're zooming in on our spacecraft on the polygonal terrain, and there's our Mecha instrument, and now a wonderful picture taken with the microscope. Tom, will you tell us about it?
Thanks very much, Peter. Yeah, this is the highest resolution image of the soil of Mars, and we're looking at a sample that was delivered using, well, a variety of sequences we had to have operating to get this soil in. This is the first sample delivery to an instrument inside a spacecraft since the Viking missions over 30 years ago. And we didn't know so much about the soil when we came down. The remote sensing satellite data told us a lot about the ice. It didn't tell us too much about the cohesiveness of the soil, and we've had to work that out as we went along. So if we go to the next slide, just to show you what we needed to do to get this soil into the microscope station. As we zoom in here, we see the microscope station, which shares its box with the wet chemistry laboratory. Those are the 4 cells on the right-hand side. And at the front, you will see a little U shape. And if we see right in front of me, we have a mock-up of the very same box. And right in a chute here, we have the substrates poking out. Now, these are what we use to capture the sample that we deliver to the field of view of the optical microscope. So during the delivery phase, the substrates are sitting outside of the box, and they're ready for the robot arm to deliver a sample. So if we go to the next image here, the next animation, we see that the way that we had the robot arm deliver the sample in this particular case was not just a dump of the soil as had been done with TIGA, but a sprinkle. And we tested this. We took 3 days in testing how to go about this sprinkle so that we would just get, we were hoping, the right amount of material on. We wanted enough material for it to be representative of the soil that we're looking at, but not so much that we would completely cover the substrates and not be able to see the individual particle sizes. So the robot arm came over the top of the microscope box, and a vibrator that is inside the scoop, which is used for when we are actually digging into hard material to loosen that. We've been improvising with that to try and see that we get a good sample to us. So if we go to the next slide, this is what actually happened. And you can see the scoop there poised just above the chute. In fact, it has just delivered the sample. You can see on the top of the box the particles, somewhat clumpy, and then just below the broad white area in the middle of the chute, those are our substrates outside, and this confirmed that we got a good sample of Mars material. So that's how we get it onto the substrates outside of the box. We now need to be able to bring that in front of the field of view of the microscope. And the next animation shows how we go about this. So we see the sample wheel in yellow sticking out of the box, and what we have to do, we have to rotate that round so that it comes round in front of the 2 microscopes that we have. Today I'll be presenting data from the optical microscope. That's the orange microscope on the right-hand side. So the wheel has come round, and then we can move the wheel into the focus position. Just in front of that orange optical microscope, we have the atomic force microscope that we hope to be bringing into operation in the next week or so. Okay, so on the next image, we can see what we have captured. So just to give what we're seeing right at the bottom of that image are the shadows from the atomic force microscope cantilevers. So they're all ready for operation. We've multiply imaged those. And if we zoom into the particles that we've collected here, this is a particle about 50 microns across, about the diameter of a human hair, a little less than the diameter of a human hair. And we see that in this case we have both a greenish part of the particle to the top. The supposition at the moment that that could be olivine. We know we see olivine elsewhere on Mars, but at the moment we can only go by the color. Below that we see the very characteristic orange coloration that we see in the Mars soil. And if we move the camera just a little bit, the optical microscope just a little bit focused out from the substrate holding this material, we can see that that clump is not, that particle is a clump of even finer particles. And we see that in the background. Particles right down to the resolution of the optical microscope. So we're going down to the individual pixels, which are 4 microns across. Okay. There's some other particles of interest as well. If we look at the, if we zoom in to a particle which is in the bottom right-hand corner here, and this is a glassy particle. If we look at this more closely, you see it's more rounded, and this may very well be a volcanic glass. And it is quite possible, if we look at the full image again of our substrate, that what we are looking at here is a potted history of Martian soil. We have the hard particles, these black glassy particles that over millions, even billions of years have slowly been weathering down, becoming iron enriched, that gives the orange material its characteristic color. And we're seeing that process captured on the variety of particles that we're looking at the moment. Now, this isn't the first set of particles that we've been able to image. We already had our substrates out to just passively collect material that was kicked up while the Phoenix lander actually came down with its retro rockets, somewhat blasting the material into the air. And we were ready to capture that. And if we look at the next slide, we see a comparison on the left-hand side of what we caught during landing, on the right-hand side of what we've got from the scoop. And the scale bar at the bottom is 1 millimeter across. What we see in the dust fall is a whole variety of very fine particles, right down to this 4 micron resolution on the left-hand side. On the right-hand side, we have what the soil has looked like once we brought it in. We can see that we've indeed got just what we were looking for, which is this field of particles well separated so that we can say something about their shape. But very importantly, we see that the clumping that was very evident when we were digging at the level of the scoop in the few top centimeters of the soil is even repeated down to the tens of microns that we're seeing here. These are tiny clumps, maybe made out of thousands of particles apiece now. But there's cohesive forces. This is obviously a very sticky material right down to the finest scale. Okay. And finally, if we look at the next, we've got a whole variety of substrates that we look at. We look at 6 substrates at a time. And this particular substrate we fabricated at Imperial College in London out of silicon. And it is a series of holes and pegs of different spacing. And the idea of this substrate is that we are able to tightly grasp the particles for future analysis with the atomic force microscope. Again, you can see the shadow of the atomic force microscope beams at the bottom of that image. And so what we have on the